A uniformly charged balloon has a negative 5 nanocoulomb charge. As a result of being charged, it sticks to the wall, and the wall exerts a 0.002 Newton normal force on the balloon. Determine the E field experienced by the balloon. I'm going to go over how to solve this problem, but what I want you to be aware of is that this problem is more than likely different from the problems you're trying to solve, and so you need to focus on the approach that I'm using and try to apply that approach to similar problems. Okay, so the first thing I'm going to do here is, especially since I'm given a force, I'm going to draw my forces. So that's my starting point, do my force diagram. So obviously, we've got gravity going down. Label that Fg, okay. We already know there's a normal force, we're told that. So it's going to point this way because normal force always perpendicular to the contact surface. Now, the whole reason it's attracted to the wall, it's sticking to the wall, is because of the electrostatic force. So I know I've got an electrostatic force going this way. And they don't mention this, but it's not falling. So I know something has to be counteracting gravity. The only option here is static friction. So those are my four forces. After doing my force diagram, I want to set up Newton's second law. Since I've got vertical forces and horizontal forces, I'm going to set it up for both the vertical and the horizontal. So if we start with the vertical, I'm going to call up positive. That means I'm going to have Fs minus Fn equals 0. Oh, Fn, apologies. That should be minus Fg, excuse me, Fs minus Fg equals 0. There we go. When I'm doing the horizontal forces, that's going to be, let's see, we'll call to the right positive, so that'll be Fe minus Fn equals 0. By the way, I want to point out, I obviously just made a mistake a moment ago, but I caught my mistake because I'm always kind of checking. Everybody makes mistakes, okay? We all make typos, we all misread something, we all quickly glance over, and in my case, because Fn was more prominent in my vision, I wrote Fn down instead of Fg. But then when I quickly looked, I saw Fn was pointing horizontally, not vertically, and I realized my mistake. So I'm always, even though you can't see this and may not be aware of it, I'm always trying to double check my work as I'm going along, and that's a good thing to do to help catch these simple mistakes we all make. Okay, so continuing on, I've got my two Newton's second law formulas here that I've set up. I know the normal force and I know the charge, and that's important because I know how to express the electrostatic force. I can express the electrostatic force, and since I'm dealing with the magnitude of the electrostatic force, I can write this as Q times E. Okay. And I'm going to go ahead and move the Fn to the other side, so that's going to be equals Fn. So what I'm using here, just so everybody's clear, is Fe equals Q times E. Okay. No vectors here because I'm just dealing with the magnitudes. I know the charge magnitude, that's 5 nanocoulombs, so that's 5 times 10 to the negative 9th. Times my E field. That has to equal my normal force, which is 0.002. Okay, so now I just solve for the E field. That's going to be 0.002 divided by 5 times 10 to the negative 9th. And when I do that, do it on my calculator real quick. I get 400,000, and that's going to be newtons per coulomb. And that's the answer. And I got to it by applying Newton's second law, recognizing, in addition to Newton's second law, recognizing that I had this relationship. So I would just use this relationship with Newton's second law.